All right. Section 1.3 is on how matter changes. Right. So, when we talk about changes in matter, we broadly classify these into two different categories. We have physical changes and we have chemical changes. Physical changes and chemical changes. Right. Physical changes are changes that do not change the identity of the substances involved. Now, here is sort of one of my go-to examples that I always use. Let's say that I take a piece of paper. Pardon the things falling in my office as I grab this. So let's say I take a piece of paper, right? And I rip it in half. What do I have now? I have two smaller pieces of paper. But this is still exactly the same stuff, right? I can still write on it. If I weren't inside, sitting in my office, I could light this on fire and burn it. I could do all the same things with this that I did when it was a single bigger piece of paper, right? Hasn't changed other than the size. So physical changes we typically think about as being things like crushing, tearing, cutting, separating, things like that. We don't change the identity of the substances. Now, chemical changes are a totally different animal. And in fact, your book doesn't use the term chemical changes. It goes straight to the term chemical reactions, which actually is a great phrasing because chemical reactions are the means by which a chemical change occurs, right? Now, what does that mean? Okay, let's look at a typical chemical or a common chemical reaction. Let's say that I take methane, right? CH4. Methane is the main component of natural gas. So you have a gas stove in your house, that's what it burns, probably, unless you have propane. If you have a gas stove, gas furnace, gas, what have you. Right. When we burn this, it combines with oxygen. And we get carbon dioxide and water. Right. Now, this that I have just written here is something called a chemical equation. All right. Let me add a few other little features onto this, though. When this happens, so first of all, methane is a gas. So I'm going to put the letter G in parentheses next to this. Oxygen, similarly, is a gas. Carbon dioxide is a gas, but water, depending on our exact conditions, we're going to go with it for here. We are going to put an L next to water for liquid, right? These are called phase labels. These, you'll have to watch me on these. I can be sloppy about putting these on sometimes, even as much as I try to remember to, but they can be super important to remember in certain types of reactions. We have four of these that we use: gas, liquid, solid, and then our fourth one actually is AQ, which we are not going to talk about now, but AQ means dissolved in water, right? Aqueous. But anyway, so in this, we have carbon dioxide, or I'm sorry, we have methane and oxygen. In a chemical reaction, they react together and they form two totally different compounds. Okay. Methane, highly flammable gas. Carbon dioxide and water, they're not. Water's a liquid at room temperature also. Totally different substances. Right. This is called a chemical equation. Now, when we look at this, everything on the left we call the reactants. Everything on the right is the products. I know that's a little bit scrunched up in there, that word is. I'll write this off to the side maybe so you can read it a little bit easier. Products. Right. Now, notice too that we have an arrow separating the two sides. The arrow indicates basically that we start here, we go to here, we can't go backwards. Now, there are ways that we can go backwards depending on the specific reaction, but we start here, we go here, right? This is a chemical equation. Now, this chemical equation, as it's written, has a problem. And if any of you all are watching this, you may see it. Here's our problem with this. Okay. So fundamentally, underlying everything that happens in chemistry, and really in any science class you take, you have this principle called the conservation of matter. We can't create or destroy matter, right? Now, this chemical equation, as it's written, violates the law of conservation of matter. Why? Because, let's go through and count this up. So, we have carbon, hydrogen, and oxygen on the left. We have carbon, hydrogen, oxygen on the right. That's all fine. But if we look here on the left, we have one carbon. We have 4 hydrogens, and we have 2 oxygens. Right? Now, we look at the right, we have 1 carbon, so that's fine. 1 carbon on the left, 1 carbon on the right. That's not a problem. But look at this. We only have 2 hydrogens. Okay? Now, how about oxygens? We have 2 in carbon dioxide. We have 1 in water. I'm going to write it this way for a very specific reason that I'll talk about here in a minute. But, so we have 3 oxygens on the right. Okay? These don't match. We need to make them match. That is a process called balancing. Right? Balancing equations. Okay. Now, when we balance equations, we cannot change the identities of the substances in here. Right? So this is CO2, it has to stay CO2. This is H2O, it has to stay H2O. So I can't balance these hydrogens by just changing this 2 to a 4, all right, if you all will follow me. What I can do is I can add what's called a coefficient on here that tells me that I have multiple water molecules. So what if I do this? What if I say that I have 2 hydrogen, or what if I say that I have 2 water molecules here? If I have 2 water molecules, that gives me 2 times 2, or 4 hydrogens. But it also gives me 2 oxygens. This goes back to why I wrote this as 2 plus 1 earlier. All right. So now I have 2 and I have 4 here, not 3. All right. Carbons are balanced, hydrogens are balanced. Our oxygens still aren't balanced, but I have 4 here. I have 2 on the left. Oxygens in this compound is O2 over here on the left. So I can fix this really easily by putting 2 as a coefficient out here. Then that becomes 4, and we're all set. And this is balanced. All right. Now, let's do another one of these. I would encourage you to practice this on your own. I am going to write this equation out, and I'm going to pause for a minute, and I'm going to encourage you all on your own to work through this and try to balance it. And then I will talk through balancing. Right. Carbon solid plus SO2 gas reacts to form. That's how we say the arrow, by the way, is we say reacts to form. CS2, carbon disulfide. Don't worry about the names. I'm just trying to use them now. Plus CO, carbon monoxide. Okay. I'll get you all started on this. We're going to just list out on each side how many of each element we have. CSO, CSO. So pause for a minute. Again, if you're working this on your own, and count up how many of each element we have on each side. Okay, on the left, we have 1 carbon, we have 1 sulfur, we have 2 oxygens. On the right, we have 2 sulfurs, we have 1 oxygen, but look at this, we have 1 plus 1 carbon. All right, so let's get to work balancing this. You know what? This is actually going to be, I would say, relatively straightforward to balance. I'm going to skip these carbons for now. And I am going to go straight on down here, and I'm going to balance my sulfurs. Okay, how can I do that? So 2 on the right, 1 on the left. So let's put a 2 there. That gives me 2 sulfurs, but that also gives me 4 oxygens. All right. Now, I have 4 oxygens on the left, I have 4 on the right. Okay, so how can I balance oxygens? Carbon monoxide is the only thing that has oxygen here. I need to put a 4 there. And that's going to give me 4 oxygens, but that's also going to change this to a 4. So now I have 5 carbons, right? Now, this is really easy to balance because carbon's just sitting over here by itself on this side, so I can just put a 5 here. And this is balanced. All right. That one was a little bit more complicated of a one, but that's okay. All right. We'll wrap that up, but there again, I encourage you to practice these. There are some practice problems in your textbook. Email me if you'd like more, and I'm happy to provide more practice problems. I'm happy to work with you to see if your answers are correct, and that will get us through section 1.3.